live session. Before going into discussions from my end, I would like to know about the questions and queries you already have. Already we have 6 weeks lecture and assignments are also on the air. So, what are the questions and queries you have? If some of the doubts I can clear online, then that probably help you. So, I would like to look into it. So, you can probably type if you have some queries there on the tutorials. I am trying to look into the forum, myself and the TAs all are trying to look into the forum, and we are also trying to answer the queries you are having. I think mostly we got few queries regarding the assignments, and probably 2 of the assignment questions the answers were given wrong, and we have corrected that and also recorded it. And apart from that, few other queries we tried to answer also. So, any particular question if you have, you can ask it. I will see if I can answer it at this stage. If the answers are need more elaborate discussion, I will probably make handout and upload it. Okay. So, I will wait for your comments for 5 minutes, 3-4 minutes. Let us see if somebody has some questions. You can see Abhishek Upadhyay and Girish are online. So, if you guys have anything specific, you can ask. Well, as of now, I didn't get any query from your end. So, let me start a small discussion, and let us try to revise whatever we have discussed over last 6 weeks. So, in this course, I actually started with very basic concepts of matrix and very basic matrix operations we discussed at the beginning, so that everybody who is attending this course should be on same page. At this course does not have any prerequisite. It is important that everybody understands different notations and different conventions regarding matrix and definition of different matrix, as well as everybody is conversant with the matrix operations. So, then our this is okay. I got a question from linearly independent matrix will give distinct eigenvalue. Is it true? Will give different. What do you mean by linearly independent matrix? Is it linearly independent columns of the matrix, right? So, this distinct eigenvalue is an interesting question, and what will of course get distinct eigenvectors and distinct eigenvalue for linearly independent matrices. It might be of importance when the yes, in a sense it is linearly independent columns will give different eigenvalues, and I'll give you a more elaborate answer, and we'll see what are the proofs for that in which cases matrices will have distinct eigenvalues, and can we have a formal proof on that. So, I'll note down this question, and I'll send you upload the answer in form of a handout, that what are the cases when the when the matrices has all distinct eigenvalues, and what are the cases when they have some of the common eigenvalues, and what will happen to the eigenvectors if the eigenvalues are all different, and what are the other cases. So, I will upload a document on that. Sure. Thank you for the question. Yeah. Anything else? And come on. I will come again on the eigenvalues and then we will probably discuss it. So, let me go to, I have noted down the question, let me go by the topics and I will come back to it. So, as I was saying that we okay. As I was saying that we are into we started with the basic matrix operations and looked into determinants and rank of the matrix, etc. That came later, but yeah, I am sorry. So, we started with basic matrix operations, and then the course is focused on matrix solvers. So, whatever matrix algebra, even like just now Abhishek asked questions about eigenvalues or eigenvectors, whatever we are doing on matrix algebra, this course has a very well defined focus which is towards the matrix solvers. We are trying to look into how matrix algebra can be useful in solving large set of equations which are matrix equations. And so, we looked into systems of linear equations and how the usually linear equations we think it in terms of rows multiplied with the coefficients are stored in rows and multiplied with the vectors which are unknown gives the right hand side of that, but we also looked how this can be expressed in terms of column combinations or column vectors. So, comment on invertibility of matrix if a matrix have all distinct eigenvalues. This is Abhishek's question, and Tejpal Singh, the session has started. He was asked when will it start. So, again so we are very much interested on all distinct eigenvalues, but invertibility, by invertibility what are you asking? So, this is to Abhishek Upadhyay. I am noting down your questions, and as I said, like I am going through a small revision on the syllabus. When I will reach eigenvalues, I will try to answer these questions. Otherwise, but if you have few more questions on eigenvalues and eigenvectors, you can write it here. Well, so then, so what we did in the to start with, we did some of the basic matrix operations and definitions of matrices, and then we looked into linear equations and saw how linear equations which are represented in matrix equation, instead of looking into row wise description of each equation, how can we describe each equation as combination of columns? Because you probably have already appreciated now that expressing matrices, expressing the linear equation as column combination and right hand side as a column space vector, right hand side B vector, gives you certain more hands over the equations, especially to see when the equations are solvable or not, and if the equations are not solvable, what to do. So, then we looked into determinant of the matrix, and we again looked from the column perspective that a matrix is a combination of the column vectors, and if the column vectors are independent, then we if they are linearly independent, then we can form a space using column vectors which has some certain value of a volume which is non-zero in the space. If these are linearly dependent, then say we have 3 columns and they are linearly independent. So, we will use these 3 as 3 vectors and we can get a 3D space which has a volume, but if 2 columns are linearly dependent, then they will give a plane and the volume of the space will be 0. A plane does not have any volume, so the volume will be 0. Similarly, for 2 columns, if they are collinear, then the area of the plane is 0. So, if columns are dependent, then the determinant will be 0, and we utilize this to see what is the rank of the matrix, how many independent columns are there in the matrix, and how can we find out the the inverse of the matrix using this concept, as well as how matrix equation can be solved using this, which is Cramer's rule. Then we went to the first matrix solver, which is Gauss elimination, and saw that Gauss elimination is a robust method, is a very ancient method and most successful method. However, Gauss elimination is computationally very costly. It takes n cube steps, and you have probably in assignments or when you are practicing try to do Gauss elimination of some 3 by 3, 4 by 4 matrix, and you have seen that it takes lot of time and lot of calculations are there. So, as calculations are there, the chance of increase in numerical errors are also high. So, so some other methods have to be looked into. LU decomposition and how LU decomposition can be applied, and there are some nice algorithm for symmetric matrices like Cholesky algorithm, Doolittle algorithm, which LU decomposition is a variant of Gauss elimination, but as it decomposes the matrix into a lower triangular and upper triangular matrix, the final solution steps are straightforward. So, but the computational cost of having an LU decomposition is significant. If we already have an LU decomposition, we can very quickly solve the matrix equation. And then we looked into Gauss-Jordan method, which is basically following very similar steps of Gauss elimination, but getting an identity matrix form from the given matrix. So, the multipliers applied with the given matrix must be matrix inverse, and finding matrix inverse. And then we saw how differential equations can be converted into difference equations and how we can get matrix equations. So, we get few more questions. If A and B are true upper triangular matrix and C is any scalar, assignment 2 question 8. Yes, assignment 2 question 8 we saw that there are another answer is right, and I think I have already the teaching assistants have decided that the marks will be awarded. So, Girish, you do not worry. Answer should be option 3A is upper triangular, AB is upper triangular, A plus B can be different from upper triangular matrix, right. If A is minus B, then of course it will not be an upper triangular matrix, and so your marks will be awarded, do not worry. Well, so then we looked into representation of matrix into physical systems into matrix, which is we started with a differential equation, mainly looked into finite difference method, which is through Taylor series expression, when it can be converted into a difference expression. And then also we looked about errors that we are making while converting a differential equation into a matrix equation, and what are the tests to confirm that the error is not significant. And then when we talk about 1D different heat conduction type of equation, 1D Laplacian equation, when we convert into a matrix form, we get a very nice tridiagonal matrix, and there is a special algorithm called TDMA or Thomas algorithm or tridiagonal matrix algorithm, in which we can solve this equation system. If we have a 2D problem or a 3D problem, we get a pentadiagonal or a septadiagonal system. And again we have alternating direction implicit method or a variant of TDMA with some of the iterative techniques which we have discussed, and we will discuss this ADI technique which we have discussed in lecture 11 in more detail. That is the beginning of third week we discussed TDMA and ADI, but ADI we will discuss in more detail at the very end of this syllabus when we will discuss about block matrix solvers or line solvers. Now, when we showed that differential equations can be converted into difference equations and we can get matrix equation out of it. When we think of differential equations, we are always posed with the question whether solution is unique and whether the solution exists. So, existence and uniqueness are inherent questions for differential equations. Therefore, the converted matrix solver matrix should also have to answer the same question whether it is whether it exists or whether there are infinite solution, that is the solution is not unique. So, we looked into the cases and from the differential equation, and then we went to the singular matrix cases, that these matrices say at EDMA with no Dirichlet boundary condition as a tridiagonal matrix without giving any Dirichlet boundary condition. When we will convert it into a matrix equation, we will get a equation where we have a singular matrix. So, there is no single solution, either there are infinite solution or there is no solution. And then we saw that these solutions, the physical system, when we solve the differential equation, these solutions are something like gives a straight line or something like that. Any point on a straight line is a solution. So, the matrix solution also should have certain properties, and we introduced vector space and vector subspace, and we discussed about different vector spaces, column space, null space, row space, left null space, etc. The interesting thing came out is that the rank of the column space and the row space is same, that is the number of independent columns is exactly same of number of independent rows even for a rectangular matrix. And also we got two spaces, null space, where if a matrix is singular, the Ax is equal to 0 will have infinite solution, A has, because determinant of A is also 0, and these infinite solutions will also form a space which is null space. Similarly, the null space of A transpose is identified as left null space, and the column vector B must lie in column space, must be a member of column space for X is equal to B having a solution. If B has certain component in left null space, it will not have a solution. So, we saw how to find out null space, how to find the solution of X is equal to B when A is singular. So, you have to first find the null space equation, and then you have to find the particular solution for X is equal to B. And then we went to linear independence, spanning of subspaces, basis dimension, the basic vector space algebra we have done. And then we went to left and right inverse of the matrix relation between fundamental subspace. So, left one inverse indicates that the matrix has sufficient independent columns, the other right inverse indicates the matrix has independent rows. So, existence and uniqueness come out of this of the existence of these inverses. And then we looked into orthogonality between the subspaces, and if the spaces are perpendicular to each other, they must be independent also, and use this property to look into that null space is orthogonal to row space, left null space is orthogonal to column space, therefore, they are complementary spaces of each other. And then we use the orthogonality concept to look into solution of Ax is equal to B when it does not have, B does not lie in column space, but A has all independent columns, and which is through normal equation or least square method. And then also we looked into Gramschmidt method, by which the columns can be converted into a set of orthonormal columns. Independent columns can be converted into orthonormal columns, which gave us QR factorization and way to solve normal equations. And also looked into eigenvectors, eigenvalues, where I am getting some questions, and let us go to Abhishek's question, invertibility of a matrix if the matrix has all distinct eigenvalues. So, a matrix, when can a matrix have distinct eigenvalues, that needs little more discussion, and I need to work it out instead of describing here, I will upload a document on that, Abhishek. But what is your question is that whether if the matrix has independent columns, does all the eigenvalues distinct? That is different than the question that so it is important to see that when matrix have independent when matrix have distinct eigenvalues, but if a matrix does not have independent eigencolumns, if some of the columns in a matrix are dependent on each other, the matrix is a singular matrix. So, we will get the determinant of a matrix to be 0. And when can a matrix have a 0 determinant? If you recall the discussion on eigenvalues, multiplication of eigenvalues, if I take product of all eigenvalues, that is same as the determinant of the matrix. So, if the determinant is 0, that means sum of the eigenvalue must be 0. Therefore, if a matrix has dependent columns, it must have at least one zero eigenvalue, and therefore it is not invertible. So, matrix with independent columns may have distinct eigenvalues. That is a different property based on which we can decide whether the matrix will have all distinct eigenvalues or whether the matrix will have some similar eigenvalue. But a matrix with dependent column will always have at least one zero eigenvalue, and therefore it will not be invertible. Does it answer your question, Abhishek, that matrices have all matrices has few dependent columns will have at least one zero eigenvalue, and therefore it will not be invertible. But when does a matrix have distinct eigenvalues, that is a different question, and I am telling you that I will discuss it with you, or I will give you a handout or discuss you this at the end of this course sometime. So, hold for that is a different question. And so, orthogonal and orthonormal is different. In a sense, orthogonal means the vectors are perpendicular to each other. Orthonormal means that each vector has a unit norm. So, the dimension of each vector is 1, that is, and the vectors are perpendicular to each other, that is orthonormal. That is, if I have two vectors A and B, I take dot product of A and B. If it is 0, then the vectors are orthogonal. And if A and B each one is of unit dimension, then the vector is called ortho. So, it has to be orthogonal, on top of that vectors should be of unit dimension, then it is called an orthonormal basis. Using echelon form, how can we use both column and row transformation? Echelon form is obtained from row transformation by adding rows with each other. So, Mr. Tejpal, I am not quite sure about your question. For using echelon form, can we? No, echelon form, the standard way of deriving echelon form is through row transformation. Column transformation, what is it? When we do row transformation, we are not changing the order of the solution vector. But when we are doing column transformation, we are changing the order of elements in the solution vector. So, you have A into column 1 plus B into column 2, say x1 into column 1 plus x2 into column 2 is equal to B, say B vector. So, if I put column 1 before a column 2, bring column 2 before column 1, so it will be x2 into column 2 plus new column 1 plus x1 into new column 2 is equal to the V vector. So, what will happen? The x2 and x1, this will be changed. So, the solution vector will there will be a permutation inside the solution vector. So, while doing this transformation on a matrix A, row transformation, or if you think of getting a lower triangular form, LU decomposition, etc., it should be done through row transformation. Getting echelon form, getting reduced to echelon form should be done through row transformation, row operations, not on column operations, because that will change the order of the solution vector. I think this answers your question. So, it is good to see that lot of enthusiasm from some of you and coming up with questions. Anything else? If you still have doubt, you can probably write it or later write in the forum. Another very important point which I want to bring today for whoever is attending this live session or whoever will look into it later, that the end semester is very much part of the syllabus. When you prepare for the exam, you have to do certain practices, you have to go through the entire syllabus, and you have to have a holistic view on the material that has been covered. And this, so the quiz end sem preparation is actually a part of syllabus, as well as when you will solve the end sem questions, you have to put certain thought about the questions. Those are not same as assignment questions. There are some more conceptual questions, more comprehensive questions are there, which will actually give you much better feel of the course. So, it is important that if you find it doable, you must register for the exam and take the exam. Girish, I don't think there is a midterm exam. There will be, Girish has that there will be a midterm exam. There will be only an end term exam at the end of this course. I don't think there is a midterm exam in present MOOC format. So there will be an end term exam which is a 100 marks exam, and there will be mostly multiple choice questions and true false questions. So objective questions will be there which will cover the entire syllabus. Part of the questions will be very similar to what you have done in your assignments. A part will be actually more simpler, which are directly from what has been discussed in the slides, whether it is called a recall type of question, whether you have you can recall what has been discussed in the slides and in the video lectures, and half of this will be your comprehension on this course. Are orthogonal sets are spanning property? So, if two vectors are orthogonal, they are independent. If we are in Rn space and we have n independent vectors, they span it. So, if we have n orthogonal vectors, they will span Rn space. If we have 3 orthogonal vectors, they will span they will not span Rn space, but they will span a 3D subspace of dimension 3 there. What is the minimum sets of span whole vector space need for dimension n? Minimum n vector. Basis the minimum number of vectors that can span a real coordinate space of dimension n should be a basis, and the basis will contain n vectors. So, a basis when all the vectors are independent as well as they are spanning. So, when we will have an independent set of vectors, they will be the minimum number of vectors which will span the entire space. So, that should be n, and orthogonal vectors are independent. That theorem we have covered in the class, and there is a very easy proof to that also. So, minimum number of independent vectors to span a space is same as minimum number of orthogonal vectors to span a space, which is n. Okay. Any question, any further question? Okay, I think I should wrap it up. It is nice to get live questions, and I tried to answer most of them. Abhishek Upadhyay has raised an interesting question. I think probably I have discussed it earlier, or if not, we will discuss. I'll look into the notes, and I told that I'll upload that when can a matrix have all distinct eigenvalues. That is a question which needs little elaboration. I will discuss that. Okay, Abhishek Upadhyay is with another question. Is it also possible through orthonormal sets? Orthonormal sets are orthogonal sets also. Orthogonal sets are orthogonal vectors when each vector has dimension 1. So, whatever you think is possible with orthogonal set is possible with orthonormal set, and whatever you think is possible with independent set is possible with orthogonal set, because orthogonal vectors are independent also. So, orthonormal vectors are also independent vectors but they are with unit dimension. So, we can form a basis using orthonormal vectors, and as a matter of fact, you look into not vector space, you look into vector algebra, vector calculus, I, j, k vectors, real R3 in R3 coordinate, real coordinate of 3 dimension, the vectors I, j, k, they are orthonormal sets, and any vector in a real 3D space can be expressed by ai plus bj plus ck. So, I, j, k and orthonormal set can span over the entire 3D space. Okay, so I think there is no more question. I cannot see any further question there. So, I will thank you all, and we will end today's session, but I will be in very soon maybe. Okay, Gramschmidt orthogonalization limitation, and I got another question. Gramschmidt limitation in computing, yes. Okay, I think you were asking about the numerical errors, computational complexity. So, when we have the vectors, Gramschmidt is a numerically unstable scheme. That means, like if you have a small number, because what you do in Gramschmidt, you take a vector, take its, you have, say you have a sequence of vectors, you take one vector, take its dot product with the previous vector. Previous vectors are already orthonormal set, and subtract that dot product from the subtract the dot products with previous vectors from that vector, and you will get a perpendicular, a vector which is orthogonal to the previous vectors, and then you normalize it. Now, when you have orthonormalized the vectors in previous in that particular sequence, each orthonormalization requires dot products, number of dot products, and then dividing by the modulus. So, in each case, when like say in nth vector, when it has been orthonormalized with respect to last n minus 1 vectors, it has to do n minus 1 dot products and then divided by the modulus of each vectors, etc. So, number of operations has already been done on it. Now, when n plus 1th vector or nth vector will be orthonormalized, it will be orthonormalized with respect to that n minus 1th vector also, which has come through all these computational steps. So, if there is some small number, and as you go through these computational steps, say there is some number 10 to the power minus 3, when you square it in order to find out the norm of that vector, this 10 to the power 1.001, this 0.001 will be squared to 10 to the power minus 6, which is again a small number, and you any computer cannot operate beyond a certain small number, maybe 10 to the power minus 8. So, it will truncate it before after that, and all these truncations compile up, and therefore, we get a large round of error, and due to this round of error we start cutting certain part of a number. Say I have a number 1.001, 2, 3, 4, 5, 6, 7, 8, after 7 I cut it. So, I dropped some part, again I square root it, or if not square root it, let us say I keep it. So, that small amount has been reduced. So, there are two orthogonal vectors which is 1.00128. Now, small amount has been reduced, so it did not remain orthogonal, it has, the angle has been changed little bit from 90 degree. I am taking another vector and trying to orthogonalize with respect to these two vectors. The second vector is already lost orthogonality with the first vector. Now, the third vector is orthogonalized with respect to first and second vector. So, it will also lose some of the orthogonality. So, when you have a large set of numbers vectors, the later vectors will try to lose the orthogonality and will end up in a set which is not orthogonal. So, we instead Gramschmidt is a computationally complex, has certain computational complexity. More will say that it is computationally unstable, numerically unstable scheme because of round of errors, because each vector is actually orthogonalized with respect to all previous vectors, and each vector, when this orthogonalization carries the errors which has been done for orthogonalization of the previous vectors. So, we went to modified Gramschmidt, where this is this is eliminated by first taking one vector and get orthogonalization one particular vector at first set with respect to one vector only, and now taking the set where one vector and all the vectors in a plane orthogonal to it, and then again orthogonalizing this, where this numerical instability is taken care of. So, instead of Gramschmidt we go to modified Gramschmidt method. What we can say is that Gramschmidt orthogonalization is a numerically unstable scheme, modified Gramschmidt is not a numerically unstable scheme, because we can handle the round of error in a more smarter way, so that they do not pile up and finally end up in giving non-orthogonal sets of vectors. Okay. I think most of the queries are answered, so I'll wrap it up for today. I'll thank you all, and we'll be again in 2-3 more live sessions. Maybe after couple of weeks or after 3 weeks, I'll come again in another live session, and probably we'll have more queries by that time. Especially I feel when we'll start the iterative solvers, the discussions will be more complex and abstract also. Right now in matrix algebra, these are not that much abstract. You write down a matrix and you can have a feel of that, except something of the vector spaces. Some part of the vector spaces might be little abstract. But when we will go to Krylov space type of methods, there will be more abstractness, and we need more live sessions. So I'll come to a live session after 2 to 3 weeks. Okay, thank you all.